Okay, here's exam 2. It's a similar format as last time where there's multiple choice, and then there's also short answer, fill in the blank part as well. Okay. This one has a few more questions in it than the last exam does, and I'll tell you when you start the exam. I think for some of you, if you're worried about time, start on the short answer part first. On the multiple choice part, there's a lot of questions that are increase, decrease, or stay the same. What happens to this if this happens? And I'll kind of take you through some examples. It's the same thing we've been doing throughout the semester. The other thing to make sure to notice is there are a couple of lab exam questions. Anaerobic power and capacity, which was the Wingate test, Marguerite-Calumet vertical jump. There's a couple questions there, a couple questions on predicted VO2 max, and then a couple questions on exercise ventilation and lactate. Okay. All right. Major topics with cardiovascular physiology. We had something. Cardiac structure and electrical conduction. Blood moves through the heart from the right side to the left side, correct? With electrical conduction, we're mainly talking about the ECG tracing. If you remember on the ECG tracing, there was a P wave, a QRS complex, and a T wave. And again, if you haven't come to one of these before, the way I usually do the review sessions, I just ask a lot of questions, and you give answers, try to think of them, so it's kind of like a real-time test prep by asking questions. So each one of those electrical events in the heart have a corresponding, on the ECG, have a corresponding electrical action in the heart. So for example, the P wave represents what electrical activity in the heart? P wave is atrial depolarization. Then the QRS complex is ventricular depolarization. And then the T wave represents ventricular repolarization. And then why don't we see atrial repolarization on an ECG? Happens during the QRS. Okay, and what those are electrical events in the heart. What mechanical events in the heart correspond with each of those ECG components? So for example, the P wave, what mechanical event happens immediately following the P wave? The atria contract. Okay, following the QRS, what happens? The ventricles contract, and following the T wave, the ventricles relax. And then in the middle of the QRS complex, when the ventricles contract, when you have atrial repolarization, that would be where mechanically the atria relax. Okay? Concept of blood pressure and flow. If I wanted to affect how blood flows into, how much blood flows into a tissue, what's the primary way the body's going to control that? It's not going to be pressure. Pressure is one of the components that affect flow. If you have a pressure gradient, you're going to either have more or less flow with the more pressure gradient you have. But the primary way the body controls it is not changing pressure, it's changing what? It's changing the radius of the blood vessel. If you remember the radius of the blood vessel in the equation I showed you, radius is raised to the 4th power. So if you double the radius, you increase flow 16 times. So it's much more effective for the body to change the radius of a blood vessel. What are some other things that can affect flow besides the radius of the blood vessel and pressure gradient? Viscosity of the fluid that you're pumping. Also the length of the blood vessel affects it. What do we primarily change to affect blood flow? Do we do we change the radius of the arteries or the veins if we want to affect blood flow? It turns out we change the arteries. It's the small arteries, or the arterioles, are the ones that change their radius. Let's talk about determinations of stroke volume, end diastolic volume, end systolic volume, and cardiac output. With stroke volume, there are 4 things that control stroke volume. They are venous return, preload, afterload, and contractility. 2 of those are going to affect end diastolic volume primarily. Which two of those factors would affect end diastolic volume, which is ventricular filling during the relaxation phase of the heart? Venous return and preload. Which two affect end systolic volume primarily? That'd be afterload and contractility. Affect end systolic volume. Some basic things to think about in terms of increase, decrease, or stay the same. Here would be some examples. What happens to stroke volume when preload increases? Preload increases, stroke volume, and these are going to be all increase, decrease, or stay the same. Preload increases, stroke volume increases. Okay, if afterload increases, what happens to stroke volume? If afterload increases, stroke volume goes down. Okay, if contractility goes down, what happens to stroke volume? Contractility goes down, stroke volume goes contractility goes down, stroke volume goes down. Because the heart's not squeezing as hard. Think about like squeezing a sponge. How much water do you get out of the sponge? If I squeeze less, I get less water out of the sponge. Same way with the heart. Does that make sense? Okay, some more trickier variations. What happens to end systolic volume when afterload increases? What happens to end systolic volume when afterload increases? Okay, end systolic volume is the amount of blood left in the ventricle after it contracts. So if afterload increases, it's harder for blood to leave the heart, right? That's the pressure which the heart has to pump against. That's my thumb example with the hose. Okay, so if afterload goes up, less blood is going to be able to leave the heart when it contracts, so the volume of blood left in the ventricle would get bigger, so it would increase. Make sense?
You said afterload was your example.
Yeah, the example I give, the analogy is if you're washing your car with a hose, okay, your thumb essentially represents afterload. It's the pressure with which the heart has to push against to eject blood. Okay, usually afterload is the easiest way to think about it is the radius of the aorta. If the aorta's aortic radius gets smaller, then afterload will go up. Okay, here's another one. What happens to end diastolic volume when venous return goes down? What happens to end diastolic volume when venous return goes down? It would go down. If venous return goes down, end diastolic volume is the volume of blood in the ventricle at the end of the relaxation phase, or how much the ventricle fills with blood when it's relaxed. If venous return to the heart goes down, it won't fill as much. So end diastolic volume will go down. In terms of defining stroke volume is equal to end diastolic volume minus end systolic volume. Remember that? Okay, let's talk about cardiac output. Cardiac output is equal to, give me a mathematical formula for cardiac output.
Stroke volume times heart rate.
Stroke volume times heart rate. What are the units on stroke volume? That's cardiac output is liters per minute. Stroke volume is milliliters per beat. Milliliters per beat are the units on that. Give me, how about some values? Can you give me some normal values? Let's talk about cardiac output at rest in a normal individual. Cardiac output at rest in a normal individual. About 5 liters per minute. What about during maximal exercise in a normal adult individual? Ballpark. I'd say 20 to 25, somewhere in there, 20 to 25 liters a minute. Okay, let's make it an elite endurance athlete. Cardiac output at rest would be about still 5 liters a minute. And why would it be the same?
VO2 is the same.
Because their VO2 at rest is the same. And what essentially drives or determines cardiac output is VO2, or oxygen uptake and demand by the body. And if you're at rest, it's basically the same whether you're a trained or untrained. Okay, but what about maximal cardiac output in an elite endurance athlete? Give me a ballpark number.
30 to 35 liters.
That's 30 to 35 is a good number. 30 to 35 liters a minute. Okay.